Good morning everyone. I am Kirti. Today I am here for aldehyde and ketones. Introduction. Aldehydes and ketones constitute two isomeric series of compounds, both of which contain the carbonyl group in their molecule and are therefore collectively known as carbonyl compound. Aldehyde has one hydrogen atom and one alkyl or aryl group linked to the carbonyl group, while ketone has a two alkyl or aryl group attached to the carbonyl group, as shown below. R and R dash may be simple or substituted alkyl or aryl groups. The aldehyde are said to be contain the functional group of carbonyl or a simple CHO, commonly referred to as aldehyde group, which while ketones contain the functional group C double bond O, generally termed as ketone group, which represent in ketones. Ketones in which the group R and R dash attached to the ketonic group are the same are termed simple ketones, and those in which R and R dash represent different groups are known as mixed ketone. The presence of carbonyl group in both aldehyde and ketone is responsible for the close similarity in their method of preparation and properties. However, due to the presence of free hydrogen atom in their molecule, aldehydes are most reactive than ketones and also different from them in certain respective structure of a carbonyl group. The carbon oxygen double bond of carbonyl group is compound of a sigma bond and a pi bond. For over in the molecule of aldehyde and ketone, the carbon atom of carbonyl group is also joined to two other atoms of a sigma bond. Thus, the carbonyl carbon is involved in the formation of a 3 sigma bond and 1 pi bond. According to molecular orbital theory, the carbonyl carbon of aldehyde and ketone make use of a 3sp2 hybridized orbital in forming the 3 sigma bond. As such, these bonds lie in the same plane with angle and approximately 120 degree between them. The pi bond between the carbonyl and oxygen is found by one sideway overlapping of a remaining half-shelled p orbital of carbon with the similar orbital of oxygen. The above discussion make it clear that the carbonyl carbon oxygen and the two atoms directly attached to a carbonyl carbon lie in the same plane. The planar nature of a part of a molecule which immediately surrounds the carbonyl carbon is supported by electron diffraction or spectroscopy study of aldehyde and ketones. According Another important aspect of a structure of carbonyl group arises from the different electronegativity of carbon and oxygen atom. Due to its greater electronegativity, the oxygen atom attracts the electron of a double bond, particularly the pi electron cloud, stronger toward itself. As a result, the electrons are not equally shared and there is a greater electron density around the oxygen than around the carbon. In other words, carbonyl group is a polar group, oxygen having a small negative charge and carbon having a small positive charge. The polar nature of carbonyl group is probably best indicated by the representing it as an resonance hybrid of the following two structures. The large dipole moment 2.3 to 2.8 diopter of aldehyde and ketone support the polar character of the carbonyl group. Comparison of a carbonyl group and ethylenic double bond. It may be interesting to note that the carbonyl group is similar to ethylenic double bond in many respects. Both of them first consist of sigma bond and a pi bond. Second, make use of sp2 hybridized carbon atom for them formation. Third, are planar in nature. And fourth, readily undergo addition reaction. However, the carbonyl group differ from the ethylenic carbon in the following respective. First, carbonyl group is polar in character while ethylenic double bond is not. Second, it is not necessary that a reagent which add to a carbonyl group must also add it to ethylenic double bond and vice versa. Third, addition reaction across carbonyl group are initiated by nucleophilic reagent while ethylenic double bond undergoes electrophilic addition reaction. Nomenclature. Aldehyde. They are named either according to the UPSC system or explained below. First, common system. In this system, aldehyde are named after the acid which they give rise to. on oxidation. The suffix ic acid is of the name of a acid is replaced by the word aldehyde. Thus, CH3CHO give acetic acid on oxidation and is therefore named as acetaldehyde. Similarly, benzaldehyde form benzoic acid on oxidation and is therefore named as benzaldehyde. This name is maintained used for aromatic or a simple aliphatic aldehyde. Second, IUPAC name. These names are given in accordance with the journal IUPAC rules. The longest chain carrying the aldehyde group is selected. The corresponding word root and the primary suffix "an", "in", and "ein" are required are written. This is followed by attracting the suffix "al" in the place of final "e". The position of substituents, if any, are indicated by substituted number. The aldehydic carbon always gets the number 1 because it is a chain terminated group. For this reason, the number of aldehydic carbon is not usually mentioned. It is taken for granted that it is must be number 1. For example, the compound is named as 3-methyl butanol. Similarly, is named as 4-methyl hexatrienol. For aldehyde in which the CHO group is attached to a ring, the suffix carb aldehyde is added to the name of a ring. For example, cyclohexane carbaldehyde, bench carbaldehyde. Common and IUPAC name of some aldehydes: HCHO, formaldehyde, IUPAC name methanol. CH3CHO, common name acetaldehyde, IUPAC name ethanol, and so on. Ketones. The two systems of naming ketones are as follows. First, common names. Common names of ketones are obtained by adding the word ketones to the name of a alkyl or aryl group present in the molecule. These names are mainly used for aromatic and simple aliphatic ketones. For example, CH3 C double bond O CH2 CH3 is named as methyl ethyl ketone. Second, IUPAC name. IUPAC name of ketones carry the suffix "on" and are given according to the usual rule. The longest chain containing the carbonyl group is selected from the name of a corresponding hydrocarbon. The suffix is replaced by one. The carbon of ketone group is assigned the minimum probability number along the state chain of a carbon atom and substituent group carrying other suitable number. For example, is named as 4-methyl pentane 2-on. Certain ketones, particularly aromatic ketones, are allowed to retain the common name. For example, acetophenone, benzophenone. Common and IUPAC name of some ketones: CH3, COCH3, common name dimethyl ketones or acetone. IUPAC name propione. CH3COCH2 CH3, methyl ethyl ketone. IUPAC name butane, and so on. Formation of aldehyde and ketones. Formation of aldehyde. Aldehyde are formed during many chemical reactions. Of these, we would describe only those important reactions which are actually used for preparation purpose. First, oxidation of primary alcohol. Aldehyde can be obtained by the oxidation of primary alcohol. However, this method suffers for a serious limitation because of the aldehyde form are further oxidized to carboxylic acid. That is, primary alcohol change in aldehyde when oxidation and further change in carboxylic acid. The oxidation of aldehyde to carboxylic acid generally takes place even with the mild oxidizing reagent. Then those reaction for the oxidation of primary alcohol to aldehyde. Therefore, it is difficult to stop the oxidation up to aldehyde state. This problem can be overcome if aldehyde form is removed from the reaction mixture by its distillation as shown as it is formed. It is often probable to do so because the aldehyde has lower boiling points than corresponding alcohol and they can be distilled away from reaction mixture. For example, 1-propanol in the presence of K2Cr2O7 and H2SO4 give propanol. Boiling point of alcohol 370 Kelvin and boiling point of aldehyde 322 Kelvin. As shown above, the oxidation agent usually employed in the above reaction is a solution of potassium dichromate in a dilute sulfuric acid. However, if the alcohol has poor solubility in water, a solution of chromium anhydride in water, acetone, and sulfuric acid is commonly used. This is known as Jones reagent. Special oxidizing agent. The above method of preparing aldehyde involving the distillation of aldehyde from the reaction mixture as shown as it is formed cannot be used in case of a higher aldehyde having high boiling point. Therefore, some special oxidizing agent has been developed for preparing aldehyde from alcohol. These are first surrogate reagent or choline reagent. It consists of a complex formed by carefully addition of CrO3 to excess of a pyridine. It gives chromium trioxide pyridine complex. A solution of above complex in methyl dichlorine oxidize the primary alcohol to the aldehyde state, that is primary alcohol change into aldehyde in the presence of chromium trioxide pyridine complex. Second, core reagent. It consists of pyridinium chlorochromate PCC for forming the mixture of chromium trioxide pyridine and HCl. It is also used in methylene dichloride solvent to convert primary alcohol into aldehyde. Third, pyridinium dichromate PDC. It is obtained by mixing pyridine, potassium dichloromate and HCl in CH2Cl3. Advantage of oxidation of alcohol with above reagent. As is obvious, advantage of using any of above three reagents is that they restrict the oxidation of primary alcohol to aldehyde stage. This is because these reagents are used in non-aqueous medium and therefore do not allow the formation of aldehyde hydrates to take place during oxidation, since aldehydes themselves are not as easily oxidized further as aldehyde hydrates. The reaction stops at aldehyde stage. In case of oxidation by usually oxidizing agents such as acidic potassium dichromate and Jones reagents, the reaction are carried out in aqueous medium. Aldehyde forms are converted into aldehyde hydrate, which are readily oxidized to carboxylic acid. Another advantage of using this reagent is the carbon-carbon double bond. If present in the starting alcohol are not oxidized, for example, 5 methyl hexaphore in 1 ol in the presence of PCC change into 5 methyl hexaphore enal. Disadvantage of using above reagent. The use of special reagent discussed above for the oxidation of alcohol lead to the formation of chromium containing waste product which are environmentally very harmless, meaning harmful. At the same time, these reagents are quite extensive and are therefore not frequently used during laboratory oxidation reaction of alcohols. Second, catalytic dehydrogenation of primary alcohol. The oxidation of primary alcohol to yield aldehyde can also be brought about by passing the alcohol vapor over copper heated 475 to 575 Kelvin. The process is generally referred to as dehydrogenation as it involves the direct elimination of hydrogen primary alcohol into aldehyde in the presence of Cu at 475 to 575 Kelvin temperature. The dehydrogenation process does not involve the risk of further oxidation of aldehyde formed. Third, reduction of acid chloride Rothenmund reaction. The partially reduction of acid chloride afford another method for the formation of aldehyde. The reaction is usually brought about by passing hydrogen through a hot solution of acid chloride in xylene in the presence of suitable catalyst. The catalyst employed in palladium partially poisonous by sulfur or quinone deposed or on barium sulfate and the reaction is stopped as soon as the evolution of hydrogen gas ceases. This helped to prevent further reduction of aldehyde formed into alcohol. Acid chloride in the presence plus hydrogen in give aldehyde plus HCl in the presence of a PDBSO4 known as Rothenmund reaction. Nowadays, lithium tetrabutoxy aluminum hydride is being used to reduce acid chloride into aldehydes. An advantage of using this reagent is that it does not affect any other easily reducible group present in the molecules. For example, para-nitrobenzenol chloride give para-nitrobenzylaldehyde. Acid chloride used in this reaction are themselves usually obtained by the action of a thionyl chloride or a phosphorus halide on a carboxylic acid that is. Thus, aldehyde can be obtained from carboxylic acid through the formation of acid chloride. Fourth, from 1,3-dithiones. The most recent method of synthesis of aldehyde is by the use of 1,3-dithiones. 1,3-dithiones or 1,3-dithichlorohexene is a non-chromatic hydroxychloro compound containing two sulfur atoms. It can be easily converted into an anion by treating with alkyl lithium. The anion act as a strong nucleophilic and react with alkyl halide SN2 reaction to form alkyl derivative of 1,3-dithiene. This derivative is hydrolyzed in the presence of Hg2 positive ions to form aldehyde. The complete sequence of reaction is shown below. 1,3-dithiene itself may be prepared by the reaction of propane 1,3-dithiol with formaldehyde in a weakly acidic medium as shown below. Propane 1,3-dithiol plus aldehyde in the presence of slightly acidic medium give dithiones. 5. Catalytic decomposition of carbonyl acid. Aldehyde can also be obtained from carboxylic acid by passing the vapor of a mixture of methanoic acid and another carboxylic acid over manganese oxide at 573 Kelvin. Carboxylic acid other than methanoic acid plus methanoic acid give aldehyde plus CO2 plus H2O in presence of MnO at 573 Kelvin temperature. Propanoic acid plus methanoic acid give propanol in presence of MnO at 573 Kelvin temperature. Some other method which can also be used for preparation of aldehyde are given below. Ozonolysis of alkene. In this method, the ozonide formed by reaction between an alkene and ozone is decomposed with a reducing agent to yield aldehyde and ketone. 1-butene in presence of ozone give cyclic structure of this, and in the presence of water and zinc give aldehyde. 7th, Stefan's reaction. Alkyl cyanide on reduction with stannous chloride and hydrogen chloride acid give rise to aldamine. Aldamine get hydrolyzed on warm with water to yield an aldehyde as shown in reaction. 8. Oxidation of methyl benzene. Aromatic aldehyde can be prepared by the oxidation of methyl benzene by different methods as shown below. First, oxidation of methyl benzene to aldehyde is usually carried out by the chromium trioxide in acetic anhydride, the gem diacetic, such that the diacetate in which the two acetic groups are attached to the same carbon atom initially formed is isolated and hydrolyzed to get the aldehyde. Simple or substituted methyl benzene give aryl diacetate and then hydrolysis to convert into aldehyde. Since the intermediate gem diacetate cannot be oxidized further, this is no chance of formation of carboxylic acid. Second, controlled oxidation of methyl benzene to aldehyde can also be carried out with carbonyl chloride or manganese dioxide. The reaction involves chromyl chloride as oxidizing agent is known as Itard reaction. For example, toluene in a presence of chromyl chloride give addition complex and then hydrolysis give benzaldehyde. Third, it is also possible to convert methyl benzene into aldehyde by free radical halogenation of methyl benzene followed by hydrolysis of the dihalide formed. For example, toluene in the presence of Cl2 give benzaldehyde plus HCl. Ninth, Gattermann-Koch reaction. This reaction constitutes a convenient method for forming aromatic aldehyde by treating benzene or other aromatic compound with a mixture of a CO and HCl in the presence of Lewis acid and copper chloride. Benzene plus CO plus HCl in the presence of AlCl3 and CuCl give benzyl aldehyde. In a similar reaction as the Gattermann reaction, HCN is used in place of CO. The aldamine initially formed is hydrolyzed to get the corresponding aromatic aldehyde. 10th, Reimer-Tiemer reaction. This is a convenient method for the preparation of phenolic aldehyde, particularly those in which the aldehyde group is present in orthoposition to the phenolic group. The reaction is carried out by treating a phenol with the chloroform and aqueous sodium hydroxide solution. Phenol in the presence of CHCl3, chloroform and NaOH at 333 Kelvin temperature give salicylic aldehyde main product plus para-hydroxybenzylaldehyde plus NaCl plus H2O. Para-hydrobenzylaldehyde formed in small quantity. Formation of ketones. The important method of preparation of ketones are described below. First, oxidation of secondary alcohols. Ketone can be easily prepared by oxidation of secondary alcohols. The oxidation is usually referred by acidified sodium or potassium dichromate, potassium permanganate, or chlorine trioxide in various solvents. Secondary alcohol in presence of K2Cr2O7 in the presence of H2SO4 give ketones. There is no risk of further oxidation of ketone taking place as ketones are not easily oxidized. Orpheneous alcohol oxidation. Secondary alcohol can also be oxidized by refluxing with acetone in the presence of aluminium isoprop oxide or aluminium tarot butoxide. The alcohol taken is oxidized to the corresponding ketone while acetone is reduced isopropyl alcohol. Secondary alcohol plus acetone gives isopropyl alcohol plus ketones. This process is particularly stable for oxidation of unsaturated alcohol and is known as Orpheneous alcohol oxidation. Second, catalytic dehydrogenation of secondary alcohol. Ketones can also be obtained by the dehydrogenation of secondary alcohol by passing through the vapor over copper heated at 475 to 575 Kelvin temperature. Secondary alcohol in the presence of copper 475 to 575 Kelvin temperature give ketone. Third, reaction of nitrile with Grignard reagent or organolithium compound. Reaction of an nitrile with either a Grignard reagent or an aluminium lithium alkyl lithium followed by hydrolysis yield to ketone. Nitrile plus Grignard reagent in the presence of ether give additional product. Then hydrolysis give ketone. Fourth, reaction of acid chloride with organocadmium compound. Acid chloride reacts with suitable organocadmium product to yield ketones. Acid chloride plus dialkyl or diaryl cadmium give ketones plus cadmium chloride. R may be any alkyl or aryl group, but R dash must be any aryl or primary alkyl group. This is because organocadmium compound containing only aryl or primary alkyl group are sufficient suitable for use. Benzoyl chloride plus dimethyl cadmium give acetophenone. These days, another type of organometallic compound known as lithium organocuprate, where R may be any alkyl or aryl group, are being increasing using for the preparation ketone for acid chloride because the reaction involved does not suffer for any drawback. Acid chloride plus lithium organocuprate give ketone plus CuCl plus LiCl. R and R dash may be any alkyl or aryl groups. Lithium organocuprate are themselves obtained by reaction between cuprate halide and organolithium compounds. Since acid chloride can themselves be obtained from carboxylic acid, the above reaction enables us to prepare ketone for a carboxylic acid. Fifth, reaction of carboxylic acid with alkyl or aryl lithium. When a carboxylic acid is treated with 2 molar equivalent of alkyl or aryl lithium followed by reaction with water, it leads to the formation of ketones. Carboxylic acid plus alkyl or aryl lithium give lithium additional product, then hydrolysis give ketones. This net reaction may be represented as For example, hexanoic acid in the presence of CH3, Li and water give 2-heptane. Ketones can also be obtained by distillation of calcium salt of carboxylic acid other than formic acid. For example, this calcium acetate distilled into acetone. 6. From 1,3-dithiones not included in a syllabus. This reaction involves the conversion of 1,3-dithiene into their dialkyl derivative in two stages and the subsequent hydrolysis of dialkyl derivative to form ketones. 7th, Friedel-Crafts alkylation. This method is especially used for the preparation of ketones in which the ketone group is attached to at least one aromatic ring. It consists in treating an aromatic compound with an acid halide in the presence of Lewis acid such as anhydride aluminium alcohol chloride. Aromatic compound plus acid chloride in the presence of anhydrous AlCl3 give ketone plus HCl. It is also possible to use an acid anhydride in place of acid chloride for intense. Benzene plus acid anhydride in the presence of anhydride AlCl3 give acetophenone. Since some other methods which can also be used for preparation of ketone are given below. The 8th, hydration of alkene. Hydration of a homologous of acetylene lead to the formation of methyl ketones. For example, 2-butane plus water in the presence of HgSO4 and H2SO4 give methyl ethyl ketone. 9th, ozone lysis of alkenes. Ozone lysis of alkenes in which the double bond is next to the position of branching of carbon chain also lead to the formation of ketones. For example, 2,3-dimethylene 2-butene give in the presence of water and zinc give acetones. 10th, acetoacetic ester synthesis. Methyl ketone can be conventionally obtained from alkyl derivative of ethyl acetoacetate, popularly known as acetoacetic ester. This method involves the conversion of acetoacetic ester into sodium acetoacetic ester by treating with sodium ethoxide, subsequently treated with alkyl halide yield alkyl acetoacetic ester. This is subjected to hydrolysis and the beta ketones acid thus obtained is heated to get a methyl ketone. For example, acetoacetic ester in presence of sodium acetoacid give sodium acetoacetic ester. In the presence of RX give alkyl acetoesters. And then finally we get methyl ketones. Physical property of aldehyde and ketone. Physical state with the exception of formaldehyde, which is a gas at a room temperature, most of common aldehyde and ketone are liquid at ordinary temperature. The lower molecular weight aldehyde has a sharp and rather unpleasant smell, but high molecular weight aldehyde and ketone are pleasant smelling. In fact, some ketones are used in perfumes. Second, boiling point. The boiling point of aldehyde and ketone are lower than those of alcohols and carboxylic acid of approximately equal molecular weight. This is due to the fact that unlike alcohol and acid, there are no effective hydrogen bonds because aldehyde and ketone molecules. However, due to the higher polar nature, this is applicable intermolecular attraction in aldehyde or ketones. As such, their boiling point are higher than those of hydrocarbon and ether as comparable molecular weight. Melting and boiling point of some aldehyde and ketone are given and below. Table 7.3 listed the melting and boiling point of some aldehyde and ketone. It is obvious that the boiling point rises with the increase in molecular weight. Third, melting point. Melting point of aldehyde and ketone do not show any regular trend with increase in molecular weight as is clear from table 7.3. Solubility. Aldehyde and ketone containing up to 5 carbon atoms are more or less soluble in water because the solubility falls rapidly with increased molecular weight. Higher member as well as aromatic aldehyde and ketone are practically insoluble. However, all aldehyde and ketone are readily soluble in organic solvent. The solubility of lower aldehyde and ketone in water is due to the formation of intermolecular hydrogen bond involving the carbonyl group as shown ahead. But the increase in the size of non-polar group attached to a carbonyl carbon does not allow hydrogen bonding to take place, so that solubility decreases sharply with increase in a molecular weight. Chemical property of aldehyde and ketone. Aldehyde and ketone are a highly reactive compound which exhibits a marked similarity in their chemical behavior. This is because of course due to the presence of carbonyl group in the presence of type of compound. But an important question which carry as is as to what make the carbonyl group so reactive and what type of reaction does it bring about in aldehyde and ketones. It would be quite appropriate to deal with the question before discussing the actual chemical reaction. Reactivity of a carbonyl group toward nucleophilic attack. The carbonyl group contain a double bond between two heteroatoms such that carbon and oxygen, since oxygen is more electronegative than carbon, the bond electrons, particularly the pi electron, are pulled strongly toward oxygen. As a result, the carbonyl group is very polar group, the carbonyl carbon being electron deficient and the carbonyl oxygen being electron rich, such that basically moreover, the carbonyl group is flat and can therefore be readily attacked from above or below in a direction perpendicular to the plane of a group. Consequently, the carbonyl group is a highly reactive group. It is quite obvious that the reaction of a polar carbonyl group could be initiated either by the attack of nucleophilic reagent on electron deficient carbon or the attack of electrophilic reaction on the electron rich oxygen. However, out of electron deficient carbon and electron rich oxygen, the former is relatively less stable. Therefore, most of reaction of aldehyde and ketone involve the initiation attack of a nucleophilic reaction on the relatively less stable electron deficient carbonyl carbon and utilizing lead to the formation of additional products. As such, these reactions are described as nucleophilic addition reaction. Mechanism of nucleophilic addition reaction. The nucleophilic addition of a carbonyl compound is initiated by the attack of a nucleophile on the carbonyl carbon. This leads to the formation of a transition state in which the hybridization of a carbon change from sp2 to sp3 at the same time of oxygen being to acquire pi electron of a carbonyl group bond as shown below. As the result, pi electron of a carbonyl bond are completely transferred to oxygen. A tetrahedral intermediate is formed in which carrier negative charge. This intermediate pick up a proton, usually from water, used as solvent to form the additional product. The attacked nucleophilic reagent can be either a negative charge ion such as Cn negative and a carboanion or a neutral molecule such as NH3 or alcohol. It may be noted that it is ability of oxygen to acquire electron or to accommodate negative charge which seem to be primary cause of a relative of a carbonyl group toward nucleophilic reagent by the attack of a carbonyl carbon. Role of acid catalyzed in nucleophilic reagent. The nucleophilic attack on the carbonyl group can be catalyzed by the presence of acid. The hydrogen ion generated by the acid repeatedly combined with the electron-rich oxygen of a carbonyl group. This leads to decrease in the activation energy for nucleophile attack as it enables oxygen to acquire the pi electron without having accommodated a negative charge shown ahead. It should be noted, however, that if the reaction solution is reagent as well, this should suppress the concentration of attack nucleophilic species and thus adversely affect the nucleophile attack. Therefore, it is important to control the pH of a reaction mixture in such reactions. It should be noted that the addition of a powerful nucleophile does not require any acidic catalyst at all. It is only the weak nucleophiles such as alcohol and ammonia derivative which need the assistance of a little acid catalyst. Relative reactivity of aldehyde and ketone in nucleophilic reaction. It has been observed that in nucleophilic addition reaction, aldehyde are more reactive than ketones and aliphatic aldehyde or ketones are more reactive than aromatic ones. This can be easily explained in terms of steric and electronic factor as shown below. First, steric factor. In the transition state of a nucleophile attack on a carbonyl carbon, the carbons start forming a bond with the attacking species and tendency to change from trigonal to tetrahedral state. Now, the larger the size of alkyl or aryl group attached to the carbonyl group, the more crowded will be the transition state. The large As the transition state get more and more crowded, the steric hindrance of group increase and the formation of a transition state become more and more difficult. Thus, the formation of a transition state would be more difficult in case of ketone than in case of aldehyde, since ketone contain two alkyl or aryl group attached to a carbonyl group, while aldehyde has one hydrogen and a one alkyl or aryl group. As such, ketone would be less reactive than aldehyde. Similarly, among the ketones themselves, those containing bigger group would be less reactive than ones containing smaller group. Second, electronic factor. In addition to the steric hindrance, electronic factor are also responsible for the greater reactivity of aldehyde as explained below. First, aliphatic aldehyde and ketones. Alkyl group has the electron releasing inductive effect, and their presence tends to disability the transition state by enhancing the negative charge developing on oxygen. Since aldehyde contains only one alkyl group while ketone has two such groups, the transition state resulting from a ketone is destabilized to greater extent than that resulting from an aldehyde. As such, the transition state is more difficult to form in case of ketone, and consequently ketone are less reactive. It can be easily understood that the presence of electron attacking subsequently on a alkyl group would enhance the reactivity of aldehyde and ketone in nucleophile reagent. Second, aromatic aldehyde and ketones and aromatic nucleus directly attached to the carbonyl group may be expected to increase the reactivity of aldehyde and ketone as it tends to stabilize the transition state due to electron withdrawing inductive effects. However, the aromatic nuclide stabilize the reactive aldehyde or ketone even more due to resonance interaction with the pi electron as shown below. The result is that alkyl group causes a net decrease in reactivity of carbonyl group. As such, aldehyde and ketone having aryl group decrease the reactivity of carbonyl group. As such, aldehyde and ketone having aryl groups directly attached to carbonyl group are less reactive than the aliphatic counterpart. It may be noted that the presence of electron withdrawing substituents such as NO2 and CN at ortho and para position on a benzene ring increase the reactivity of aromatic aldehyde and ketones. Electron donating groups ROHOR has a opposite effect. Acidity of alpha hydrogen B side providing a site for nucleophilic addition of aldehyde ketone. The carbonyl group is also responsible for the acidity of alpha carbon atom. In the presence of a base, a hydrogen attached to a alpha carbon atom can split off in the form of a H positive ion to form a anion. The carb anion thus formed account for a many reaction of aldehyde and ketone. The addition nature of alpha hydrogen and its removal in the presence of a base can be attributed to the fact that the resulting carbanion is resonance stabilized by reacting with the carbonyl group as shown below. It is interesting to note that the participation of a carbonyl group in resonance stabilization of the carb anion is also due to the ability of oxygen to accommodate the negative charge. Ionization of beta and gamma hydrogen of saturated aldehyde or ketone is not possible as the resulting carbanion would not be resonance stabilized. Having discussed the fundamental aspect of reactivity of aldehyde and ketone, let us now deal with the various chemical reactions actually undergoes by these compounds. Nucleophilic addition reaction. A large variety of nucleophilic reagents can attack the carbonyl group to yield additional compound in which the carbonyl carbon is bonded to some atom of attacking reagent. The addition compound thus formed may itself represent the final product, or it may undergo a subsequent elimination or subsequent reaction to furnish a more stable product. Nucleophilic addition reaction leading to the formation of a new bond between carbonyl carbon and the atom of some other element such as oxygen, nitrogen and sulfur. First, addition of sodium bisulfite. Nearly all aldehyde and many ketones, particularly methyl ketones, react with a saturated sodium bisulfide solution to form crystalline solid referred as a bisulfide additional compound. In this compound, carbonyl carbon get bonded to a sulfur of the attacking reagent. It is a reversible reaction, but on using saturated solution of a sodium bisulfide, the equilibrium is shifted to the right and the additional product get precipitated. Aldehyde or ketone reacted with a sodium bisulfide give aldehyde or ketone bisulfide compounds. Ketone containing bulky group do not react with NaHSO3 due to steric hindrance. Mechanism. The reaction involves nucleophilic attack of a carbonyl carbon of bisulfide ion and the complete process may be depicted as shown. Mechanism. The reaction involves nucleophilic attack of carbonyl group bisulfide ion and the complete process may be depicted as shown below. The bisulfide addition compound decomposes on warming with dilute acid or base to give back the original carbonyl compounds. Therefore, the formation of bisulfide compound is used for the purification of carbonyl compounds, particularly aldehyde for non-carbonyl impurities. Second, reaction with ammonia derivative. Aldehyde and ketone undergoes nucleophilic addition with certain compounds related to ammonia such as hydroxylamine, hydrazine, phenylhydrazine, semicarbide. The additional compound initially formed eliminated a compound of a water to yield compound containing a double bond between carbon and nitrogen. As such, these reactions are also termed as additional elimination or a condensation reaction. If we represent the ammonia derivative by journal formula H2NG, where G may be OH, NH2, NH6H5, NHCO, NH2, etc. The formation of final product may be depicted as aldehyde or ketones plus ammonium derivative give initial additional compound and final product is C double bond Ng. The product formed are usually crystalline solid having sharp melting point and are used for identification of aldehyde and ketone. Moreover, as this product can be decomposed by boiling with dilute mineral acid to regenerate the parent carbonyl compound. They can also be used for the purification of aldehyde and ketones. Mechanism. All the ammonia derivative represented by formula H2NG are basic compound having a lone pair of electron on nitrogen. They act as weak nucleophile reagent and their reaction with carbonyl group is catalyzed in the presence of acid. The hydrogen ion protonated the carbonyl oxygen and as a result the carbonyl carbon is very readily attacked by the basic nitrogen compound. The adduct thus formed subsequently changed to the final product as shown below. Reaction condition control of pH. It must be pointed out that while using acid as a catalyst in the reaction, it is very important to have proper acidity in the reaction mixture. If the reaction mixture is made highly acidic, the hydrogen ion being to protonated the attack ammonia derivative too. The protonated derivative H3N positive G does not have any unshared electron on nitrogen and is no longer nucleophile. This naturally means that too much acidity would decrease the rate of a reaction rather than catalyze it. In other words, the reaction medium should have just the right acidity or pH to ensure maximum rate of reaction. Ammonium derivatives used as a nucleophilic reagent in this reaction are usually employed in the form of their salts such as hydroxyamine, hydroxychloride, and hydrazine sulfide in the presence of sodium acetate. For this salt, the attacking nucleophilic reagent is produced in a state as shown below. Hydroxylamine hydroxychloride plus sodium salt, sodium carboxylate salt, ये sodium acetate give H2OH plus NaCl plus carboxylic acid. The important reaction of ammonia derivative are discussed below. First, reaction with hydroxylamine, aldehyde and ketone react with hydroxylamine to form amines. Aldehyde plus ketones in the react with hydroxyamine in slightly acidic medium give aldoxamine या ketoxamine. Second reaction, reaction with hydrazine. Aldehyde and ketone react with hydrazine to form hydrazone. Example, propanolaldehyde plus hydrazine give propanylaldehyde hydrazone. Third, reaction with phenylhydrazine. Reaction of aldehyde and ketone with phenylhydrazine result in a formation of phenylhydrazone. Example, benzylaldehyde plus phenylhydrazine give benzylaldehyde phenylhydrazone. In place of phenylhydrazine, substituted phenylhydrazone are also frequently employed. The most commonly used substituent phenylhydrazone is Substituted phenylhydrazines are also frequently employed. The most commonly used substituted phenylhydrazine is 2,4-dinitrophenylhydrazine Beride reagent, which readily reacts with aldehyde and ketone to form yellow, orange, or red PPT of a 2,4-dinitrophenylhydrazone, completely known as 2,4-DPN. DNP. Fourth, reaction with semicarbide. Both aldehyde ketone react with semicarbide forming semicarbones. Aldehyde plus semicarbide zone in slightly acidic medium give aldehyde or ketone semicarbides. Reaction 5 with ammonia. The reaction of aldehyde or ketone with ammonia are no important. Most of aldehyde initially form additional product with ammonia known as aldehyde ammonias. These compounds are unstable and lose water to form aldehydes, which is in turn get polymerized. Aldehyde in presence of formaldehyde react with the differential to form hexamethylene tetramine, which is used as a urinary antiseptic under the name urotropine. Benzaldehyde react with ammonia to form hydrobenzamide. Ketones generally give complex polymerizing product with ammonia. Reaction of aldehyde and ketone with primary and secondary amine to form imines and imines is discussed later in chapter 10. Third, according to addition of alcohol, aldehyde and ketone react with alcohol in the presence of anhydrous acid catalyst such as HCl gas to form ethanol compound called acetals. Acetals contain new bond between carbonyl carbon and oxygen atom of the alcohols. Example: acetaldehyde plus alcohol in the presence of HCl gas give acetal plus water. The product formed by the reaction between ketone and alcohol were earlier called ketones, but now the term acetal is used for the product formed for aldehyde as well as ketone. Mechanism: to start with the molecule of alcohol, add to a carbonyl group of aldehyde to form a hemiacetal. With a few exceptions, the intermediate hemiacetal is not stable enough to be isolated. On the other hand, under the catalyst influence of acid, the hemiacetal is readily converted into the stable acetal. It may be noted that the conversion of hemiacetal into acetal involves the replacement of OH by an alkoxy group, and its mechanism is similar to SN1 mechanism for the formation of ether or from an alcohols. Formation of cyclic acetal. Both aldehyde and ketone react with ethylene glycol in the presence of para-toluene sulfonic acid (PTS) to yield respectively cycle acetal. For example, ethanol plus ethylene glycol in the presence of PTS give cyclic acetal plus water. Use of acetal as protecting group. Unlike aldehyde and ketone, acetal are very stable to bases but are hydrolyzed back to aldehyde and ketone upon treated with acid. Therefore, this formation is used as a mean of protecting a carbonyl group in certain reacting where it may otherwise interfere with a desired reaction. Protection is the process of preventing a group from taking part in an interfere with a desired reaction. Undesired reaction by converting it into a new, less reactive group from which it can be regenerated at a later stage. For instance, let us imagine that we want to carry out the reduction of a ester group of a keto ester into an alcoholic group. A reducing agent which bring about the reduction of ester group would normally reduce the keto group as well. Therefore, selective reduction of ester group is not possible. The problem can be solved by first converting the ketone group into acetals. The resulting acetals in then subjected to reduction with lithium aluminium hydride. When ester group would be reduced to alcohol, but acetal would remain unaffected. The acetyl group is then hydrolyzed back to keto group with aqueous acid. This is illustrated below by considering the formation of a 4-hydroxypentane to all from ethyl 4-oxopentanoate. Nucleophilic addition reaction leading to the formation of carbon-carbon bond, carbon anion as the nucleophile reagent. We would now take up a reaction in which carbon anion constitute the attacking nucleophile reagent. Most of these reactions are of a great synthetic importance since they lead to the formation of carbon-carbon bond. Fourth, addition of a hydrogen cyanide. Hydrogen cyanide add to almost all aldehyde and ketone to form alpha hydroxynitrile, usually known as cyanoanhydride. Acetaldehyde plus HCN give acetaldehyde, cyanohydride. Hydrogen cyanide is produced in situ by dissolving NaCN or KCN in water and then slowly adding a mineral acid to adjust the pH of solution at about 10. Mechanism. The reaction involves the initial nucleophilic attack on carbonyl group by a strong basic carbon anion such that cyanide ion. The process is complete by the attacking of a hydrogen ion to oxygen. Cyanohydride are useless synthetic substances because they can be easily converted into other compounds having new functional group as illustrated below. First, the alcoholic part of cyanohydride can undergo acid catalyzed dehydration to form unsaturated nitrile. For example, acetaldehyde in presence of acid give acryl nitrile. Second, they are readily hydrolyzed to form carboxylic acid. For example, CH3CHOHCN. Acetaldehyde plus water in presence of acid give lactic acid plus ammonium. Third, the nitrile group present in them can be reduced into a primary amine by catalytic hydrogenation. For example, benzaldehyde cyanohydride in presence of hydrogen and nickel give 2-amino 1-phenyl ethanol. Fifth, addition of Grignard reagent. Grignard reagent and other organometallic compounds react with aldehyde and ketone to form additional products which are readily decomposed by water, preferable in the presence of an acid such as HCl or H2SO4 to yield alcohol. Aldehyde or ketone with Grignard reagent give additional product, then hydrolysis give alcohol. Mechanism. In the formation of aldehyde, protect the nucleophile anion portion such that the organic part of a Grignard reagent add to a carbonyl carbon while the remaining portion get attached to oxygen as depicted below. This is followed by hydrolysis of additional product. In it may be pointed out that depending upon the starting aldehyde or ketone, the alcohol obtained as the final product may be primary, secondary or tertiary alcohol. Formaldehyde yield a primary alcohol, other aldehyde give secondary alcohols while ketones furnished tertiary alcohols. Formaldehyde react with Grignard reagent give primary alcohol. Aldehyde other than formaldehyde react with Grignard reagent give secondary alcohol. Ketone react with Grignard reagent give tertiary alcohol. 6. Addition of salt terminal alkyne. When treated with terminal alkynes in the presence of sodium and lithium aluminium. Addition of sodium salt of alkynes to the carbonyl group take place. The product formed on acidification give rise to alcohol which also contain carbon-carbon triple bond. For example, ketone plus हाइड्रोजन जैसा कि अल्काइन साल्ट है सोडियम का, ये इससे रिएक्ट करवाएंगे तो ये एडिशनल प्रोडक्ट बन जाएगा. इसका हाइड्रोलिसिस करेंगे तो 2-methyl but3-ionol बन जाएगा. The alkanol formed above can be converted into other compound by reacting involve the OH group of a carbon-carbon triple bond. Mechanism. The reaction involves the nucleophilic attack on carbon anion of a terminal alkyne on the carbonyl group as shown below. 7th, reform stick reaction. The reaction consists in treating an aldehyde or ketone with an alpha brom ester and metallic zinc in the presence of dry ester or benzene. The additional product initially formed is decomposed in the presence of dilute mineral acid to yield beta hydroxy ester. For example, acetaldehyde plus ethyl alpha beta acetate plus zinc in the presence of ester give additional product, then hydrolysis give ethyl beta hydroxybutyrate. Mechanism. The mechanism of reformatory reaction is similar to Grignard reagent. Zinc is used in place of magnesium because organic zinc compound, being less reactive than Grignard reagent, react only with carbonyl group of aldehyde or ketone and not with ester group. The complete mechanism of a reaction may be depicted as follows. Beta hydrogen ester undergoes acid catalyzed hydrogenation to form alpha beta unsaturated ester. For example, ethyl 3 hydroxybutanoate in the presence of acid give ethyl but 2 in 8. 8. Idol condensation. In the presence of a dilute base, two molecules of an aldehyde or a ketone having alpha hydrogen atom combine to form alpha beta hydroxy aldehyde or beta hydroxy ketone. The hydroxyaldehyde obtained from acetaldehyde was originally named aldol, such that aldehyde alcohol, and consequent the reaction came to known as aldol condensation. For example, aldehyde plus acetaldehyde in the presence of base give 3-hydroxybutanol. Propanol aldehyde, propanol aldehyde in the presence of base give 3-hydroxy 2-methyl-pentanol. It may be noted that in every case the product contains a carbon-carbon bond between the carbonyl carbon alpha molecule and the carbon of alpha second. Mechanism. The base remove an alpha hydrogen from aldehyde or ketone molecule to form resonance stabilized carbanion or enolated ion. This ion, being strongly nucleophile, attacked the carbonyl carbon of a second molecule of aldehyde or ketone to yield an anionic intermediate. The intermediate then extract a proton from water to form the aldol. The complete mechanism is illustrated below by consideration for the example of acetaldehyde. It is more important to note that aldol condensation can occur only due to the acid nature of alpha hydrogen of a carbonyl compounds. These aldehyde or ketones such as formaldehyde, benzaldehyde or benzophenones which do not contain any alpha hydrogen atom do not undergo simple aldol condensation. This is because such aldehyde or ketone cannot resonance stabilize carbanion. Synthetic important. The beta hydroxyaldehyde or beta hydroxyketones obtained from the base catalyzed aldol condensation are easily dehydrated on warming with acid to form alpha beta unsaturated carbonyl compound. Alpha beta unsaturated carbonyl compound in turn can be oxidized to alpha beta unsaturated acid to reduce selectively to alpha beta unsaturated alcohol. Therefore, aldol condensation commands considerably synthetic importance. It can be employed for the preparation of beta hydroxycarbonyl compound, alpha beta unsaturated carbonyl compound, alpha beta unsaturated carbonic acid, alpha beta unsaturated alcohols, etc. Cross aldol condensation aldol condensation can also take place between molecules of two different aldehyde or ketone or an aldehyde or an ketone. Such an aldol condensation is referred to as cross aldol condensation if both the reacting carbonyl compound containing are usually quite different to separate. Therefore, such a reaction is seldom carried out. However, if one of the reactant does not contain any alpha hydrogen, the reaction can yield a mixture of only two products. Moreover, by a suitable choice of experimental condition, it is possible to suppress the formation of one of the products so as to get only one compound as the main product. For example, if aldehyde acetaldehyde, which contain alpha hydrogen, is solely added to a mixture, benzaldehyde, which does not contain any alpha hydrogen, and aqueous alkyl. The final product is mainly Simon aldehyde, obtained by a dehydration of initial formed beta hydroxyaldehyde. Similarly, reaction between acetone which contain alpha hydrogen and formaldehyde which does not contain any alpha hydrogen yield mainly 4-hydroxy 2-butanol. It may be pointed out that in cross-aldol condensation, the aldehyde or ketone lacking in alpha hydrogen cannot form the attacking carb anion. It merely serves as a site for the nucleophile attacked by the carb anion formed by the other reactant. Aldol condensation can also be take place in the presence of acid. However, the acid catalyst condensation is not so effective and additional compound initially formed readily undergoes dehydration to alpha beta unsaturated carbonyl compound as well as the final product. For example, ethanol in the presence of acid give additional product than lose water form carotene aldehydes. Mechanism: acid catalyst aldol condensation takes place in acidic medium. In the presence of acid, the carbonyl compound is partially converted into enolic form as shown below. The enol acts as a nucleophile and attacks a second molecule of protonated carbonyl compound from an intermediate. This slows a proton to form a condensation product. The condensation product thus formed readily undergoes acid catalyst dehydrogenation to form alpha beta unsaturated carbonyl compound as the final product. Ninth, calcium reaction, a calcium reaction. This reaction is especially case of a cross aldol condensation and may be defined as base catalyst condensation of an aromatic aldehyde and an aliphatic aldehyde or a ketone to form alpha beta unsaturated aldehyde or ketones. For example, reaction between acetaldehyde and benzaldehyde in the presence of aqueous alkyl yield mainly Simon aldehydes. In above cases, reaction initially two products are obtained. Is the self-condensation product of acetaldehyde, while the other is the cross-condensation product, which is the main product. This product is which beta OH group is activated by phenyl group loss water immediately to form alpha beta unsaturated aldehydes. Similarly, reaction between benzaldehyde and acetone in the presence of aqueous alkyl yield benzaldehyde. Mechanism of a reaction similar to the base catalyst aldol condensation. 10th, benzoin condensation. Aromatic aldehyde which do not contain alpha hydrogen atom cannot undergo simple aldol condensation. However, in the presence of potassium cyanide, they undergo self condensation in a different manner to produce product known as benzoins. For example, benzaldehyde in presence of cation give benzoin. Mechanism: the reaction is generally believed to proceed as followed. 11th, Birkin reaction. Closely related to aldol condensation is the Birkin reaction, which involves the addition of acid anhydride to aromatic aldehyde in the presence of base. The base commonly employed in a sodium salt of carboxylic acid from which the anhydride is derived, and the additional compound initially formed utilize yield an alpha beta unsaturated acid. For examples, benzaldehyde plus acidic anhydride in presence of sodium carboxylate salt at 450 degree temperature give cinnamonic acid. Cinnamic acid. Only aromatic aldehyde are used in picric reaction because they do not contain alpha hydrogen. Aldehyde containing alpha hydrogen undergoes the more repeat self condensation in the presence of base. Mechanism: in the presence of base, the acid anhydride lose a hydrogen ion from alpha carbon to form a anion, which add to a carbonyl group of aldehyde. The resulting ion, after protonated, form an aldol-like product. This product undergoes a dehydration in the presence of acid anhydride to mix anhydride, which get hydrolyzed to form the alpha beta unsaturated acid. The complete mechanism is shown below by considering the reaction between benzaldehyde and acetic anhydride in the presence of sodium acetate. 12th, Cannivogal reaction. This is another reaction close related to aldol condensation. It involves the condensation between an aldehyde or ketones and a compound having an active methylene group such as a malonic acid, malonic ester, and acetoacetic ester in the presence of base, which is usually an amine such as pyridine or piperidines. In general, the reaction may be represented as aldehyde or ketone plus active methylene compound in the presence of base give this final product. For example, aldehyde plus malonic acid in the presence of pyridine give 1 2 3 1 3 carboxylic acid. 2 ethyl 1 3 dicarboxylic acid. The condensation product formed above can be decarboxylated to get an alpha beta unsaturated acid. Mechanism: the base remove a proton from the active methylene compound to form an resonance stabilized anion. This attacks the carbonyl carbon. The ion thus formed undergoes protonation followed by dehydration. The mechanism may be depicted by considering the reaction between an aldehyde and acetoacetic. 13th, Mann-Nitsch reaction. This is the reaction between an aldehyde and amine and an active methylene compound, which is usually an inolable ketones. The aldehyde usually take an formal aldehyde and the amines commonly employed in a dimethylamines. The reaction can take place in neutral acid and alkyne medium, and the product form is popularly known as Mann-Nitsch base. For example, inolable ketones plus aldehyde plus amines give Mann-Nitsch base. Mechanism: to start with, formal aldehyde react with amines to form an iminium salt. The iminium ion get attacked by inolation ion of attacking methylene compound to form the final product. Mann-Nitsch reaction can proceed through different mechanisms depending on the reactant and condition employed. The above mechanism is base catalyst reaction. 14. The Wittig reaction. This is a reaction between aldehyde or ketone and a type of a compound known as phosphorus yielding to form substituent alkenes. The phosphorus yields generally used are alkyldine triphenyl phosphenes. R and R dash may be equivalent to hydrogen or alkyl or aryl group. The overall reaction may be represented as, for example, benzaldehyde plus methylene triphenyl phosphate gives styrene. It is clear that the reaction results in the replacement of a carbonyl oxygen by the group CRR-. Formation of phosphorus yielding or Wittig reaction. The phosphorus yield requires the reaction are themselves obtained by the action of a base on a suitable alkyl triphenyl phosphate halides prepared from alkyl halide and triphenyl phosphine. The base removed a proton from an alpha carbon atom of alkyl group of a phosphine salt to generate the yields as shown below. The base generally employed in above process is methylene sulfurine carb anion generated by the reaction between sodium hydride and dimethyl sulfoxide or some organelle lithium compounds such as N-butyl lithium or phenyl lithium. The solvent commonly used is dimethylformamide DMF or tetrahydrofuran THF. For example, we have triphenylphosphine plus methylene iodine give methyl triphosphylphosphine. Isolated but are directly made to each with the aldehyde or ketone in a solution form. Mechanism: the phosphorus yields a resonance hybrid of the following contributed structure. Due to negative charge on carbon, the yield exhibits carb anion character and initiates the nucleophilic attack on a carbonyl carbon. The resulting additional product known as bitrine undergoes elimination of a triphenyl phosphine oxide to yield the alkene directly or a cyclic intermediate as shown below. The carbonyl compound as well as the yield used in the Wittig reaction may carry suitable substituent, and therefore the reaction can be used for preparing widely variety of compound containing carbon double bond carbon in the desired position. In case of formation of alkynes which can show geometrical isomerism such that the reaction give a mixture of both isomer in the trans isomer predominant. Halogenation of inolations. Aldehyde or ketone no include in the syllabus. It is in the presence of a suitable acid or base. The alpha hydrogen or aldehyde and ketone which contain alpha hydrogen can easily halogenated at these hydrogen to form alpha haloaldehyde or ketones. It may be pointed out that the aldehyde or ketone have alpha hydrogenation undergoes tautomerism to form enols and are therefore called inolable aldehyde or ketone. The halogenation reaction of such aldehyde or ketone proceed by different mechanisms depending upon whether the reaction is carried out in the presence of acid or base as discussed below. 15th, base prominated halogenation in the presence of a suitable base such as OH negative ion and CH3CO negative ion. One or more alpha hydrogen of a carbonyl compound get replaced by a corresponding number of halogen atom. For example, acetone plus Br2 in presence of OH negative means in basic medium give alpha bromoacetones. Mechanism: bromination of acetone in the presence of base was one of the earlier halogenation reaction of a ketone to study in detail. The rate of reaction was found to be independent of the concentration of bromine, while it was observed to directly proportional to the concentration of ketone and the base. This was attributed to the formation of carb anion intermediate as the rate of determining stem followed by the rapid bromination process as depicted below. In support of above mechanism, it has been shown that under similar condition, a ketone undergoes chlorination and iodination at exactly the same rate as it undergoes bromination. This is in the keep with the formation of an common intermediate in the rate determining step of all these processes. The above mechanism was further supported on the basis of stereochemical and isotopic studies of a halogenation process. Since the base is actually consumed during the halogenation reaction, the reaction is often referred to a base induced and base prominated rather than merely base catalyst. Halogenation of unsymmetrical ketone in the base induced halogenation of unsymmetrical ketone of a type RCH2 C double bond O CH3 halogenation occur at a methylene rather than methylene group. This is because the electron reducing inductive effect of R group serve to decrease the acidity of hydrogen attached to the methylene group, while the hydrogen attached to the methylene group are not affected. This leads to the preferential formation of a carb anion which is more stable than second. Further, base-induced halogenation of monohalogenated ketones, say um, uh, bromoketones, occur preferentially at the carbon atom already halogenated, provided that it is still carried a hydrogen atom. For example, this is given in below. The electron withdrawing halogenation atom carried by the halogen substituted carbon atom makes the hydrogen still attached to the carbon more strongly acid and therefore more readily abstract by the base. Moreover, it also helps to stabilize the carbon ion with the comparison to fourth. The preferential formation of a this compound naturally lead to the formation of a product shown above. 16. Acid catalyzed halogenation. The halogenation of a carbonyl compound is also catalyzed by acid mechanism. Like the halogenation reaction in the presence of a base, rate of acid catalyst halogenation is also independent of the concentration of halogen but depending upon the concentration of ketones and acid. Moreover, here too a given ketone undergoes halogenation at the same rate irrespective of the nature of halogen employed. All other conditions being of course employed in keeping with above observation, the mechanism of acid catalyzed halogenation involves the formation of an enol intermediate as the rate determining step of reaction. The enol formation repeatedly react further with the halogen as depicted below in the considering halogen of acetones. It may be noted that the acid merely serves as a catalyst and is not consumed during the reaction. Halogenation of unsymmetrical ketone in an acid catalyst. Halogenation of unsymmetrical ketones such as RCH2 C double bond OCH3 halogenated take place preferentially at the methylene group. This is explained on the basis of fact that enol in which COH double bond C grouping is more substituent are more stable and therefore more rapidly. Now RCH2 C double bond O CH3 can form the following two enols. First, lesser substituted, less stable. Second, greater substituted, greater stability. Evidently, the enol which ultimately lead to halogenation at methyl carbon is more stable than an enol first, which would result in halogenation at methyl carbon. Therefore, halogenation preferentially occur at methyl carbon. It is to be noted that in acid catalyst process, further halogenation of monohaloketones does not take place readily. This is because the halogen present in the monohaloketones, say CH3 CH3 C double bond O CH3 CH2X tends to withdraw electron toward itself. This makes the initial uptake of proton by the carbonyl group step first in the mechanism very difficult, so that enol is not easily formed. It may be pointed out that the aromatic aldehyde or ketone can also undergo electrophilic substitution reactions such as halogenation, nitration and sulfonation involving the aromatic nucleus. It may also be recalled in this connection that carbonyl group is deactivating and matter directing. For example, benzaldehyde plus Cl2 in the presence of FeCl3 give metachlorobenzaldehyde. Reduction. Aldehyde and ketone can be readily reduced to form various products depending upon the nature of reducing agent employed as discussed below. 17. Reduction of alcohols. Aldehyde can be reduced to primary alcohol and ketone to secondary alcohol either by hydrogenation in the presence of catalysts such as nickel, palladium or platinum, or the reducing agent like lithium aluminium hydride or sodium borohydride. Aldehyde in the presence of hydrogen, lithium, nickel or a lithium aluminium hydride give primary alcohol. Ketone give secondary alcohol. Propanoin aldehyde give n-propyl alcohol. Mechanism. The mechanism of this reaction has already been discussed in chapter 3. Mervin Pondorf Verily reduction. It is commonly used reaction for the reduction of ketone to a secondary alcohol. The reaction is carried out by heating the carbonyl compound in isopropyl alcohol in the presence of aluminium isopropoxide, also known as Mervin Pondor Verily reaction, and distilling of acetone from the reaction mixture. The other functional group, if any, present in the carbonyl group remain unaffected. Ketone plus isopropyl alcohol in presence of aluminium isopropoxide give secondary alcohol acetone. Distillation of mechanism. The mechanism of this reaction has already been discussed in chapter 1st. 18. Reduction of methyl group. The carbonyl carbon in aldehyde and ketone can also be reduced to methylene group to form hydrocarbon. This is generally achieved by the following two methods. First, Clemenson reduction. The involves the reduction of aldehyde and ketone with zinc amalgam and concentrated HCl. For example, acetophenone in presence of zinc amalgam and HCl give ethyl benzene. The reaction work well for ketones but not for aldehydes. Mechanism. Several mechanisms have been proposed for this reaction. One of the purpose mechanism is as follows. Second, Wolff-Kirschner reaction. In this method, the aldehyde or ketone is heated with hydrazine and a strong base like potassium hydroxide or potassium terbutoxide. For example, cycloanone in the presence of hydrazine and KOH gives cyclohexane. Mechanism. The reaction is initiated for the formation of a hydrazone of aldehyde or ketone which undergoes significant change as shown below. First, since Clemenson reduction involves the use of a concentrated HCl, it cannot be used for the reduction of a carbonyl carbon, which may be also contain some other group suspected to attack by acid. On the other hand, Wolff-Kirschner reduction cannot be used for compound which may contain some alkyl synthetic group as well. Second, these reactions are particularly used for in the synthesis of alkyl benzene containing straight alkyl chain consisting of many carbon atoms. For example, N-hexyl phenyl ketone in the presence of zinc amalgam and HCl give N-heptyl benzyl. Third, reduction with HI. Aldehyde and ketone can also be reduced to corresponding hydrocarbon by heating with HI in the presence of red phosphorus. For example, aldehyde or ketone plus HI in the presence of red phosphorus give alkene plus water plus 2 I to मतलब iodine. 19. Biomolecular reduction. In the presence of magnesium, usually employed in the form of amalgam, aldehyde or ketone undergoes biomolecular reduction to form symmetrical glycols, generally formed as pinacol. The name of pinacol was initially employed for the glycol obtained from acetone, but it has been come to use for all symmetrical glycols. Mechanism. Pinacol reduction involves the formation of bond between two carbonyl carbon and proceed through the following mechanism. Manganese donate one electron each to a molecule of a carbonyl compound to form an adductive. This contains two unpaired electrons, one on each carbonyl carbon, which unite to form a carbon-carbon bond to furnish the magnesium salt of pinacol. The salt is ultimately hydrolyzed to form pinacol. The mechanism is usually in the sense that it involves initially attack on oxygen rather than carbon. Reductive amination. Many aldehyde and ketone change into amines or treated with hydrogen and ammonia in the presence of a catalyst such as nickel. The process is known as reductive amination and probably proceed through the intermediate formation of an amines. Aldehyde or ketone in the presence of ammonia give amines, then reduced in the presence of hydrogen and nickel give primary amines. The possibility of a further reaction between aldehyde or ketone and the amines formed can be restricted by employing suitable portion of a reaction. Oxidation. The behavior of aldehyde and ketone toward oxidizing agent constituting the main different in the chemical properties of these two classes of carbonyl compounds due to free hydrogen atom attached to a carbonyl carbon. Aldehyde are very readily oxidized even by mild oxidizing agent to form carboxylic acid having the same number of carbon atom as the original aldehyde. Ketones, on the other hand, resist oxidation and get oxidizing only by strong oxidizing agent. The oxidizing reaction of aldehyde and ketone under different conditions are given below. Oxidation of aldehyde. A. As stated above, aldehyde are readily oxidized by usually oxidizing agents such as KMnO4, KTCrO2O7, H2SO in the presence of H2SO4 or H2CrO4 chromic acid and dilute HNO3 to form corresponding acid. For example, aldehyde in the presence of ethanol in presence of K2CR2O7 and H2SO4 give carboxylic acid means ethanoic acid. Mechanism of aldehyde oxidation with different oxidizing agents are not well established. In the chromic acid oxidation of aldehyde, it is believed that the aldehyde is the first hydrated to a gem diol. The diol get oxidized via the formation of chromium ester as shown below. Reducing character. Since aldehydes are very easily oxidizing even by mild oxidizing agent, they act as powerful reducing agent as illustrated by the following reaction. Reduction of tolerance reagent. Tolerance reagent in an ammoniacal solution of silver nitrate which contains silver in a form of silver ammonia complex ion. On adding an aldehyde to this reagent, the aldehyde is oxidized to carboxylic ion which in ammoniacally solution form the ammonia salt of acid. The silver ammonia complex is reduced to metallic silver which get decomposed as a silver mirror on the sides of a tube containing the solution. The reaction is therefore referred to as the silver mirror test. Aldehyde plus toluene reagent give ammonia salt plus silver mirror plus ammonia plus water. Secondary reduction of a Fehling solution and a solution. Bentic solution. Failing solution is obtained by mixing equivalent quantity of a solution of a copper sulfate and a solution of sodium hydroxide and sodium potassium titrate known as Rochelle salt. The resulting solution containing a copper titrate complex which furnishes a small concentration of cupric ion. Bentic solution is comparable to filling solution and is obtained by mixing copper sulfate solution with a sodium curate. This is contain a copper curate complex which furnish cupric ion. On reacting an aldehyde with filling or a bentic solution, the blue color of a cupric ion is discharged and a red ppt of cuprous oxide is obtained. The reaction may be depicted as the above reactions are not given by ketones since they are not easily oxidized and therefore do not act as a reducing agent. Therefore, these are used to detect the presence of aldehyde group and to distinguish aldehyde from ketone. Oxidation of ketones. It has already been stated that ketones are not easily oxidized. This is because oxidation of ketone invariably involves cleavage of a carbon-carbon bond and therefore it can be brought about only by a strong oxidizing agent. The important oxidation reaction of ketone are as follows. Oxidation to carboxylic acid, strong oxidizing agent such as the acid defied potassium dichromate and concentrated nitric acid to yield a mixture of acid each containing lesser number of carbon atom than the original ketone. The reaction involves the attack only at the carbon atom adjacent to the carbonyl group. For example, 5 carbon atom in presence of K2Cr2O7 and in the presence of H2SO4 give 2 and 3 carbon atom carboxylic acid. In case of asymmetrical ketone, the attack takes place preferentially at the adjacent carbon carrying less number of hydrogen atom. For example, attack takes place in the arrow place, so the product form is ethanol and ethanoic acid and ethanoic acid. If both adjacent carbon atom has the same number of hydrogen atom, carbonyl group remain linked preferentially to the smaller alkyl group known as Popov's rules. Second, haloform reaction. An important oxidation reaction of a ketones is a haloform reaction of a methyl ketone. It consists of reacting a methyl ketone with halogen in aqueous sodium hydroxide. As a result, the ketone is oxidized to form the sodium salt of an acid containing one carbon atom less than ketone and at the same time haloforms such that chloroforms, bromoforms or iodoform is produced. The overall reaction may be represented as uh, halogens plus NaOH give sodium hypohalides plus NaOX. When a halogen is dissolved in aqueous sodium hydroxide, the solution formed containing sodium hypohalides are shown below. The reaction is also used as a test for a methyl ketone when employed for the purpose. The hypohalides used is sodium hypoiodide because the iodoform formed separated out as a yellow ppt that can be easily identified. The reaction is termed as iodoform reaction and are may be depicted as follows. Mechanism. When methyl ketone is treated with halogen in aqueous sodium hydroxide, halogenation takes place at a carbon of a methyl group forming a trihaloketones. The carbonyl carbon of these trihaloketones is then attacked by hydroxy ion. As a result, cleavage of a carbon-carbon bond between carbonyl carbon and the trihalomethyl group take place. This ultimately leads to the formation of a carboxylate ion and haloforms as depicted ahead. Apart from methyl ketone, haloform react is also given by compound containing such group that will form the methyl ketone structure. Under the condition of this reaction, the secondary alcohol of a type ketone Ketone also respond to the reaction since they are easily oxidized to methyl ketone structure. Acetaldehyde is the only aldehyde and ethyl alcohol is the only primary alcohol that also exhibits this reaction. Third, Bailey-Villiers oxidation. This reaction involves the conversion of ketone into ester by reaction with per-acid such as per-benzoic acid, per-acetic acid, and trifluoroper-acetic acid. Formation of ester takes place due to the introduction of an oxygen atom from the per-acidic beta carboxylic carbon and alpha carbon. Cyclic ketone yield lactones in the reactions. Mechanism. The reaction is catalyzed by a acid and involves the addition of per acid to carbonyl carbon of ketones. The most important step in the reaction is the migration of a group R from carbon to electron deficient oxygen as shown below. In case of unsymmetrical ketone, the tendency of group to migrate called migration aptitude to electron deficient oxygen is in the order tertiary alkyl, secondary alkyl, phenyl, primary alkyl, methyl. In case of substituted aryl group, the order is paramethoxyphenyl, paratoluene, phenyl, parachlorophenyls. The migration aptitude determine the final product from formed in the reaction. For example, in the oxidation of acetophenone with the perbenzoic acid, the final product is ester because phenyl group has a greater tendency to migrate to the electron deficient oxygen than methyl group. It may be seen that the net result of Barley-Wiley oxidation is that an oxygen is inerted in between carbon and carbonyl group and adjacent carbon of a group having greater migrating aptitude. Cannizzaro reaction. This is a self-oxidation and reduction or a disproportion reaction which is undergoes by aldehyde having no alpha hydrogen. It consists in treating such an aldehyde with a concentrated aqueous or alcohol solution of sodium or potassium hydroxide when an alcohol and a salt of carboxylic acid are produced. For example, formaldehyde plus concentrated solution of sodium hydroxide give methyl alcohol plus sodium formate. Mechanism. This mechanism involves the addition of hydroxy ion to an aldehyde molecule to form an anion. This anion transfer a hydride ion to a second aldehyde molecule as shown below. Crossed Cannizzaro reaction. Cannizzaro reaction can also take place between two different aldehydes not having alpha hydrogen. It is known as cross Cannizzaro reaction and can lead to the formation of four different products. However, if one of the aldehyde is a formaldehyde, the product consists of almost exclusive sodium formate and the alcohol derivative from the other aldehyde. Test of aldehyde and ketone distinction between them. First, test of aldehyde and ketone. Aldehyde and ketone can be detected by following tests. First, they form crystalline addition product with sodium bisulfate solution. Second, they form yellow or orange color derivative with 2,4-dinitrophenyl hydrazine. Second, distinguishing between aldehyde and ketone. Aldehyde can be distinguished from ketone by the following test. Aldehyde form a silver mirror on a washing with toluene reagent but ketone do not. Second, aldehyde give red PPT on warming with Fehling solution or benthic solution but ketone do not. Aldehyde give a pink color solution with CJF reagent but ketone do not. CJF reaction is a solution of para-rhodyl aniline hydrochloride dichloride by passing SO2 into it. Third, distinguish between methyl ketone and other ketone. Distinguish between 2-pentanone and 3-pentanone. When a methyl ketone is treated with sodium hypoiodide such that iodine in the presence of sodium hydroxide, a yellow pipette of iodoform is produced. Other ketones do not give this test. The test known as iodoform test is used for distinguish between methyl ketone and other ketones. For example, 2-pentanone can be distinguished from 3-pentanone by this test as follows. Treat each compound with a little iodine and a few drops of sodium hydroxide. 2 pentation produce a yellow PPT of iodoform while the air is no reaction in case of a 3 pentation. Fourth, distinguish between acetaldehyde and benzaldehyde or formaldehyde. When treated with a little iodine and a few drops of sodium hydroxide, acetaldehyde give a yellow PPT of iodoform, but there is no reaction in case of benzaldehyde or formaldehyde. It may be recalled that iodoform test is given by only this compound which contain this group. In generally, aliphatic aldehyde can also be distinguished from aromatic aldehyde by Fehling solution. The former reduce Fehling solution while the latter do not. Thank you. This chapter is complete.